A struggling IB physics student once said, the fact that KQ divided by R squared, KQ divided by R, KQ divided by R, and KQ divided by R squared all apply to different things feels different to me, laugh out loudly. And indeed, these equations are very similar, but they apply to different things. So, in this video of Host Academy, I'm Samuel by the way, we'll work on Coulombs law and explain how does this equation different and where can they be applied. Charges, like positive or negative charges, can be quantified with the use of the unit coulombs. For example, a positive charge can be quantified as x coulombs with the unit c, and a negative charge can be quantified by negative x coulombs. Obviously, x can be whatever number you want. However, in order to actually quantify the interaction between the charges, for example, what is the force of repulsion in these two like charges, we can use the Coulombs law, which states that Fe, electrostatic force, equals to KQ divided by R squared. So in this equation, K means the Coulomb's constant, which is just a number that you can find on the data booklet. Q represents one of the charges, for example, this charge, which is in the unit of coulombs. The small q equals to another charge that sits in the interaction, which again can be measured by coulombs. And r is just the distance between the two charges in meters. So this equation, by just plugging in numbers, you can find the force of attraction or repulsion between them. However, one thing that we should add is that Fe also equals to EQ, where E equals to the electrostatic field strength of one of the charge, and Q equals to a charge of another charge. So what does this actually mean? And what is the difference between the electrostatic force between the two, and the electrostatic field strength of one of them? So you can look at this. First of all, what is force? Force is basically just the force caused by the two different charges, the force between them. And it's just simply a force that denotes what the quantity of the force between them. So it takes account of both of the charges. Therefore, the equation is KQ divided by R squared, which involves two of the charges, like the charge of two of the charges. However, E is different, as in that E is the intensity of the electric field of one of them. So as you can see in this, like the drawing thing here, you can imagine one of the charge being here, and the electric field strength referred to, let's say, a certain point to here. There's one coulombs of positive charge. Then what will be the force it receives? Therefore, this only takes account as one of the charges, and the equation will be KQ divided by R square. Yeah. So as you can see, this only cares about one of the charges, and if we want to take account of how the actual force between the two charges, we have to multiply this by Q, and then we'll get Fe, the electrostatic force. We write this. We can compare this into EQ equals to Fe. So basically E will be equal to KQ divided by R squared. So this is basically a two laws of Coulombs laws that you need to know for SL. And so let's jump into some Excel content right now. Or we can just do some practice questions. Okay, so imagine you have two charges, one positive charge here and one negative charge here. One of them have the charge of +5, and one of them have the charge of, let's say, -1. So first, what is the electrostatic force between them? This question is simple, as we can just, okay, I forgot to mention, the distance is 5 meters, let's say. Okay, so how do we calculate this? Pretty simple, just plug in the equation. Fe equals to KQ divided by R squared. Therefore, you can just plug in numbers as 8.99 times 10 to the power of 9 times plus 5, which is the big charge, and times -1, which is a small charge, divide by r squared, which is 5 to the power of 2. And I don't have a calculator by hand, but just plug in this equation in a calculator and you get the answer. So it's not really that deep. However, one thing that I want to note is that it's the negative signs. So as you can see, if one of the charge is positive, one of the charge is negative, the resulting electrostatic force will be negative, because positive times negative equals negative, right? So this will be negative x. So negative x generally means that the charges are attracted to each other. However, imagine if both of the charges are negative, then your equation will be k times negative q times negative q divided by r squared, which, since both of the charges have negative, it will turns out to be a positive number, and still become positive x, which means that the forces are repulsing each other. So the forces going away from each other. Yeah. So that's basically what it is. And if you want to calculate let's say the electrostatic field strength for one of the charges, then we can just use F equals to EQ and just divide the F by Q. You get E. Or, since we know that F equals to KQQ divided by R squared, and you're dividing this by Q, the Q cancels out, so you may also know that E equals to KQ divided by R squared. So you again plug in the numbers and you'll get the answer. Okay, so that's basically for the SL, which is the easy stuff. And now let's move to HL. Okay, so now for the HL contents. And most of the HL contents are about energy, with the equation of EE equals to KQQ divided by R, not R squared. Okay, so this electrostatic energy basically means the work required to bring a charge from infinite to a certain point with a certain distance from another charge. So to understand this, we must first understand the concept of 0 at infinity. So what does it basically mean, 0 at infinity? So let's get this equation and take the limits of it with r approaching to infinity. Since r is like you're dividing by r, if r approaches infinite, then the energy will be 0. Then the energy will approach 0. Will also approach 0. So what does it mean? In order to bring a charge from infinity to a certain distance from another charge, we must do work against the repulsion of the another charge. So this will be the electrostatic energy, which is represented by KQ divided by R. So if this is electrostatic energy, then what about electric potential, also called as voltage? So this can be explained similarly to how we explained the electrostatic force and electrostatic field strength. So a similar thing here. So electrostatic energy is the energy to bring a charge from infinity to another charge. So in another sense, you are basically taking account of the charge of both of them. Therefore, in the equation, it will be KQ divided by R, where both of the Q's are taken into account. However, for electric potential, it will be the energy to bring a positive test charge to another charge. So what does that mean by positive test charge? Generally, a positive test charge just means that a positive charge with 1 coulombs. And instead of another charge that we are changing, like it could be whatever charge, this time it's a fixed charge, so that we can know how many joules are there per Newton. Therefore, for equation, we will generally just use KQ divided by R without taking account of Q. And the units will be joules per coulombs, which means that per every coulomb, X joules of work is required to bring this to another charge. Yep. Well, this is R. So this is really similar to the to this thing we had here, because it's basically the same thing. One of the equations takes account of both of the charges, and another equation only takes account of one of them. It's like the potential one of them in terms of joules per coulombs. So let's do some quick practice questions. Actually, before that, I forgot to mention. So how does KQQ divided by R squared, which is the electrostatic force, relates to KQQ divided by R, the electrostatical energy? So to relate these two things, you can use the equation of that of that work equals to Fs, where S is a distance, which is R in this case. So since electrostatic energy is basically the work required, right? So we can just write KQ divided by R here. It's basically the same thing, or you can call it E to electrostatic energy. This will be equal to KQQ divided by R squared, which is an electrostatic force, times S, distance, which can be written as R. So this R will cancel out, like the power of the denominator R will cancel out with the R. So now we know that EE will be equals to FE times R. So this is basically the relation between the two. And in order to find one of them, if you have another one, just divide it by R, or multiply this by R. Yep. However, I have to mention this because this was shown in the quiz. That's the difference. Sometimes you can't just convert them because one of them, because electrostatic energy is a scalar unit, while electrostatic force is a vector. For example, if you have two negative charges here, and you want to find the force, if you want to find let's say the electrostatic field strength in here, since the force in point A, I would say, since the force is a vector, and they have the same distance, they will cancel out. So it will end up the E will end up being 0. Okay. However, if we're talking about electrostatic potential, which is the voltage, it doesn't cancel. So it doesn't cancel, and instead it stacks up. So the voltage will be adding these two KQ divided by R times 2. Yeah, so that's the difference. So if you see basically some factor additions or sometimes you have to break it down to components, don't just convert them using this equation, okay?